Hey y'all, today on McGregor H2O, I'm joined by Garry Queen, a professional engineer and regional sales manager at Dynamatic. Gary works closely with utilities on variable speed pumping applications and brings a strong applications engineering perspective to eddy current drives. We're getting into what these drives actually do, why they still matter in 2025, and how utilities can retrofit them or modern SCADA and energy saving control strategies. There's a lot of noise in the industry about electronics, VFD, harmonics, and supply chain issues. Eddy current drives give utilities a different path forward, and Gary's here to break it all down for us. So, welcome, Gary.
Hi, Taylor. Thanks for having me. I sincerely appreciate the introduction and warm welcome. Eddy current drives, or ECDs, were the drive of choice for many years. In the 90s, many thought that ECDs were dead as a technology because of the market share that variable frequency drives had captured due to their much lower cost. While it had been known for a while that VFDs had electrical issues such as harmonics and other issues with regard to their output power, these issues caused many folks in the water industry to reevaluate the use of the ECDs because they don't have the electrical issues. They're easier to use, understand, program, maintain, and they outlast VFDs easily by 6 times longer or greater.
Yeah, thanks for that intro, Gary. Let's jump right into the 10,000-foot view here. In simple terms, what is an eddy current drive?
Well, quite simply, an ECD is an electromagnetic drive. I say it that way because the drive itself is mostly mechanical, but it is electrically controlled.
Okay. And so many operators have probably seen the name Dynamatic, but they may not know the physics. How would you describe how an eddy current clutch and drive actually transmit power?
Fantastic. Good question. The term eddy current clutch and eddy current drive are actually synonyms. So just so folks know, if you say clutch or drive, we're talking about the same animal. The power is basically delivered by the motor, and the motor's running at full speed. The motor is attached to a drum inside the ECD, and the drum is also running at full motor speed. Control is done by varying a DC voltage to the coil on the ECD rotor. This creates a magnetic field between the drum and the rotor within the ECD. If the magnetic field strength is at full, the output rotor of the ECD matches the motor speed. If the DC voltage is reduced, the magnetic field weakens and the ECD rotor slows down.
That seems pretty straightforward. Yeah. So what sets this type of drive apart from VFDs and soft starters in the way it controls speed? I guess you kind of touched on that in this last question, but yeah, if you could break that down more for us.
Sure. The VFD takes AC power, converts it to DC, and there's an inverting bridge on the output stage of the VFD, and it chops up the DC and sends it to the motor in high-speed pulses called pulse width modulation, or PWM for short. PWM is regulated so that the inrush current to the motor is reduced while producing 150% starting torque. The high-frequency pulses can cause a whole bunch of electrical issues, though. Soft starters reduce voltage to the motor by using electrical switches, which reduce the voltage during startup. This reduction keeps the motor inrush current lower, which is beneficial for large motors. However, soft starters do not have the capability of producing 150% or higher starting torque, and torque is typically around 40% for the soft starter. The eddy current clutch or drive, on the other hand, again, as I said before, it takes DC power and applies it to the coil within the ECD rotor. And by reducing the voltage to the coil, it slows down the motor. And hence you have full power to the motor being passed through the VFD and similarly through the soft start, but you only have a fraction of that passing through the eddy current controller, which is approximately about 1% of the total horsepower rating.
Okay. Yeah, then great. So we'll jump into the next section here. If large water and wastewater facilities still have installed bases of eddy current drives, why are they lasting so long?
Well, there's a couple different reasons for that, mainly because ECDs are air-cooled. They're more resilient to temperature conditions than VFDs. ECDs are mostly mechanical, as I said previously. VFDs are all electrical and use semiconductor power devices as well as semiconductor logic chips and processors. Most VFDs are manufactured such that they need to be kept at 104 degrees Fahrenheit or lower, Typically, most control systems integrators will design VFD panels to stay at 94 degrees Fahrenheit. When you get to much bigger motors, instead of the 1, 2, 3, 4, 5 horsepower types, you get up to several hundred horsepower, they typically require air conditioning, which means that the VFDs typically have to be put into electrical rooms that are cool. The ECDs, they don't require that. They're all air cooled. We do ask users to bring in fresh air and exhaust it to the outside world, which is pretty easy for most of these facilities to do. So being impervious to high temperatures, the ECDs typically last longer. The controllers for the ECDs are called ECCs, or eddy current controllers. They're typically rated from minus 40 degrees Fahrenheit to 70, stand corrected, from minus 40 degrees centigrade to 70 degrees centigrade. So they're pretty impervious to higher temperatures as well.
That's good news for the southeast where we're all at. It gets a little hot down here in the summer.
You bet.
So when a plant operator tells you this thing just runs, what would you say is really behind the reliability?
Well, unlike VFDs that require cooling, typically from air conditioning, the ECDs don't require that. And in terms of maintenance, it's pretty simple. ECDs require that you check lubrication on them and actually re-grease them once every 2,200 hours of operating time. So that's approximately 1/4. So every quarter, you need to lubricate your eddy current drives. And then at the same time, you need to do for the large drives, typically 300 horsepower and above, they'll have brushes for the slip rings to transmit DC to the coil. You need to check the brushes biannually. The brushes do wear. They're typically good for about 7,500 hours of operation, and there are springs on there that you can adjust to change the amount of force being applied to the brush on the slip ring.
So simplicity is really the key thing here. That's what it sounds like.
Pretty much.
Yeah, so let's jump into the next segment. We got retrofit and integration with modern SCADA. So I know there's a lot, everyone's kind of going into the electronic age, and a lot of operators want better speed control without ripping out mechanical equipment. How do modern Dynamatic controls retrofit into older eddy current drives?
If they're Dynamatic, we can actually have a perfect replacement. In fact, we can rebuild any unit that's been built since 1931. And also, most of the eddy current competitors over the years, and believe it or not, Dynamatic was one big name in the eddy current era, if you will. There was another company called Electrical Machinery, but there are others still out there, even Hyundai and Toshiba and Yaskawa, and some of the more popular names today actually made eddy current drives. And many of them we can repair for customers, but we can also replace them, and the footprint, assuming they're using T-frame AC motors, is pretty much a drop-in. Holes may need to be adjusted, but pretty much they're the same size or extremely similar.
Sounds good. So we can be a resource for pretty much any eddy current drive application. That's what it sounds like.
Correct.
So for plants that rely heavily on SCADA, what type of integration or what does integration look like? Is it complicated, or I guess, can you break that down for us?
Sure. Typically, SCADA implies supervisory control and data acquisition. So that means that you're communicating with your motor controls typically. And we start pretty simply. All of our eddy current drives come with RS-485 serial communications, pretty standard. There's no fuss, no muss there. A lot of folks, though, like to collect data at much higher speeds and typically on an Ethernet type platform. So if customers need that kind of speed, we certainly can accommodate it. Some of the protocols we offer are Profinet, Ethernet IP, and Modbus TCP IP.
Sounds like you've got the big ones covered, so that's good news.
We figure about 95%.
Oh, absolutely. So yeah, I guess we could jump into this question that kind of overlaps here, but it's still good to clarify. What type of signals can you accept? Can the drive accept?
Well, there's discrete I/O, which would be contact inputs. They can be dry contacts from control relays, or they can be actually from a PLC with digital outputs using relay cards or even 24-volt DC. Also, for discrete I/O in terms of outputs, we have several relay type outputs folks can use for control downstream or for making decisions. And we have analog inputs and outputs which are typically 0 to 10 volts DC and 4 to 20 milliamps. And they're programmable in software. And also there's a jumper on the main control board that can be changed as well.
Yeah, so my motto is the more data, the better. That seems to be, it's good to know what you're dealing with. So that's great. If you had to do a retrofit cost comparison to a full VFD replacement in terms of capital and downtime, what are we looking at?
Well, to start with, ECDs are more expensive than VFDs because they are precision machined drives. They're not electronic. The initial costs up front are not a complete story because you have to consider the advantages of each technology over time. Costs can vary considerably depending on project specifications. What we do is we like to work with customers and help them calculate their total life cycle costs and compare the various alternatives for their jobs. So it's hard to say. If you had apples to apples, the costs are very similar, but depending on specifications, they can be very dissimilar. So the best thing to do, in our opinion, is to do a life cycle cost. That way you can take a look at an amortization period over 20 or 40 or 60 years and see what your total costs are over the life of the project.
Right, yeah, exactly. So the ECDs, they last a long time. The typical VFDs are what, 15 years, and these could last up to 50?
VFDs are designed using what they call a DC bus. AC is converted to DC, and DC is cut up and sent to the motor as PWM. So the full motor power passes through the VFD, and the Achilles heel or the strength of the VFD is basically the capacitor bank that stores the DC power in the drive. And if you pick up most manuals from any manufacturer, they'll pretty much tell you that the life of those capacitors is approximately 100,000 hours, which translates to 11.3 years. Now, that's given the statistical life of it, but there are also operational concerns that affect the life of a VFD as an example. One is how well is it taken care of? Is it kept below 104 degrees Fahrenheit? Have you made sure there was no dust collecting on the heat sinks and stuff like that? So what our customers tell us now, and we can only go by what they tell us, they say that most of the VFDs have about a 5 to 8 year life. Okay, so with the ECDs, like I said, the maintenance is pretty simple. It'd be really nice if customers were to take an air hose and blow dust out of them and stuff like that. But overall, taking care of them is definitely doing the lubrication, checking the brushes, because once these eddy current drives are put in place, they have to be anchored. They have to be anchored if they're horizontal, and similarly, if they're on vertical turbine pumps, they have to be anchored properly there too. So that drives all of it.
Okay, great. Well, that actually kind of leads us into our next section. We got the field serviceability and long-term support here. So, question I have, which you kind of were just covering, but the big advantage is that these drives are mechanically simple. So you kind of went into it, what the field service actually looks like.
Well, anytime a customer is having any kind of difficulty with an eddy current, we encourage the customers to reach out to us because we'll be glad to walk them through all the things that they need to look at because it might be something simple that's going on. As far as units that are returned, we find that 99% of them that are returned, and there aren't many, but they're returned because they haven't been properly lubricated. So again, we go back to the issue of greasing the bearings every 2,200 hours. We encourage customers to have a PM schedule for that. We are working on some updates to our controls, which are actually going to be able to send SMS messaging to maintenance managers and other key personnel to let people know that, lubrication time is approaching. There's a bunch of other stuff coming out in our future models, and this probably isn't the right for it, but it is coming. The other part of the maintenance is to check brushes biannually as a minimum. Brush wear is important, especially on the large units, 250 horsepower and lower. We use what we call a monocoil, and so there are no brushes that transmit the DC to the coil within the eddy current. In the future, which is another project we have ongoing with an upgrade to our eddy current drives, is we're creating what we call a rotating transformer, which will actually use to transmit. It'll actually be AC across the transformer, and then it'll be converted to DC on the rotor to apply DC to the coil on the rotor. So a lot of good things happening. But again, we encourage customers to give us a call when they're having any kind of issue because we like to help them out and keep them running.
Awesome. Yeah, definitely. That's great. It's always good to have resources at the factory that know exactly what is going on and common points that uh, could be need to be looked at. And especially having a text message tell you, "Hey, it's time to lubricate," and that just makes it easy for people to remember. So I guess, yeah, here's a good question. How fast can a plant typically get a unit back online during maintenance compared to like an electronic drive?
Well, it really depends on how far the maintenance went down because if it's just standard preventive maintenance, we can come up just as quickly as it takes to apply power to it and give it the permissive to run. If a unit has been removed for service, of course, you have to go back and going back to a statement I made earlier, the key thing to making an eddy current last literally forever, or at least a human lifetime, is to properly anchor them. Vibration is not a good thing. So you've got to anchor them properly, literally zero vibration. You do that, you're in business. Now, how long does that take? Well, it depends on how skilled the techs are at anchoring them and checking vibration, alignment on the couplings and stuff like that. So really that's a question I just can't give you a couple hours on, 3 hours, half a day. It
Right.
depends on the customer. But we are there as a support mechanism for the customer to give them not only support, but we also can send service people out to give them a hand as well.
Good to know. Good to know. I might have to call them and go in and see some customers. So that's great news. Yeah. So that can lead us into our next section here, the no rare earth magnets and supply chain benefits. So, we were speaking about this before. So a good question here, though, is let's talk about the magnets. A lot of modern motor technologies rely heavily on rare earth materials, but eddy current drives don't. So why does that matter?
Well, rare earth magnets are interesting. They really are. They're extremely magnetic, and as a kid, you probably remember taking magnets and playing with them and have them chase or follow, depending on which way you're doing it, or run away from the poles. You got like poles facing each other. They're going to try to separate. Or dissimilar poles are going to attract and all that. You got the same issue with rare earth magnets, but they're typically very, very magnetic. In terms of motor control, in order to decrease the field, to change the amount of field strength, you'd have to separate the magnets by moving them. And usually that requires something like a linear actuator or some kind of way to pull the magnets apart. Within an eddy current, we use what we call an electromagnet. So basically what we have is a piece of iron, and we take copper and we wrap around that iron, and it turns into a magnet when we pass current through the copper wire. And we can control the amount of the magnetic field between the rotor and the drum within an eddy current just by simply changing the voltage. To use a rare earth, we'd have to change the entire design scheme to be able to move the magnets away from each other. However, the future is not written about what we can do as we move forward. Technology is evolving, and there may be things that may be uncovered that would give us the opportunity to actually use rare earth magnets in eddy currents, because there are some that believe, like me, that with the rare earth magnets, you could gain efficiencies you don't currently have at the moment. But as I said, the future is unwritten on that. Pardon me. The future is unwritten on that at the moment, but it is going to change. I'll be willing to bet every dollar I have on
Oh
that.
yeah, efficiency is what everyone's always chasing. So I'm sure you guys are going to keep innovating and keep, bringing us new stuff. So even on this technology that's been around for many years, it's always good to think about it in a different way. So yeah, I mean, how does avoiding rare earths affect pricing stability, repairability, and long-term sustainability for utilities?
Well, again, as I said, we believe that the electromagnet is the way to go for today because the technology doesn't exist for us to use rare earths easily. Electromagnetics have been around a really long time. You'll see all kinds of magnets used in the recycling business for cars and stuff like that. So it's an extremely reliable technology. It's real easy to create an electromagnetic, so that reduces costs. And when you take a look at the number that have been operating out in the field for more than 50 years, we believe it speaks for itself.
Hey, that's the test of longevity. That beats anything in my book, especially since you pay for it once.
The way it goes, for Sure.
Yeah, so let's jump into the southeast. We both live down here in the southeast, and that's where all my customers are. So many plants in this area have aging infrastructure, limited electrical rooms, and tough humidity conditions. How does the eddy current drive hold up to that?
Well, actually, you do pretty well. The one thing that you would really worry about most would probably be the eddy current controller or the ECC. But the good news is they're smaller and they take up less space. Because of their temperature ratings of minus 40 to 70 degrees centigrade, we can close them up in NEMA 4, NEMA 4X. You want to do stainless, we can do that too. Fiberglass, we're pretty flexible. NEMA 3R, it's certainly not a problem there. They're actually less impacted by heat. And you'd find that true in the electrical business too with VFDs. When they have a much higher temperature rating, they do better in the southeast as well. But not all manufacturers make VFDs rated for 50 or 60 degrees C. Now, PLC manufacturers, on the other hand, the PLCs are typically rated between 70 and 80 degrees centigrade. So you don't have quite the same problem with them. Overall, ECDs and ECCs are a good investment for those that want easy to understand and operate, ruggedly reliable and easy to maintain in a very harsh environment, especially in the southeast in July.
So yeah, that's a good way to lead into this next question too. Are there situations where the eddy current drive is clearly the better choice over a VFD?
Well, yes, there are a number of them, and it has to do with space. If you're really jammed up for space, you may have to opt with a VFD because they can wall mount those things. And that, as we said earlier, all the power for the motor passes through the VFD, so that is one advantage for them. ECDs require space, whether it's vertical space or horizontal space. But if you've got the space and you're running a vertical turbine or a split case pump, there is no choice, especially if you're a municipality wanting to pump either waste or fresh water. The eddy currents will be there long after the VFDs have been replaced, and most often after the VFDs have been replaced 3 to 5 times.
That sounds like a good ROI to me. Let's
Well,
see, are
most
there
of the
any
numbers turn out pretty good.
in helping engineering firms or municipalities with those calculations for the life of is pretty incredible too. Not everybody offers that, so it's good to have those numbers in front of you and be able to make a good decision. But yeah,
I
let's
agree.
we're just gonna probably move into closing here, Gary. We definitely hit a lot of topics. So what should operators look for when evaluating whether to rebuild, retrofit, or replace?
Well, the first thing to do is gather information, what they have for power, voltage, space, control, communications, and then take all that information, combine it with a wish list of what they want. We don't want customers to make a decision on moving to one technology or another and then have buyers remorse after the fact. We've seen that in the field. We've seen it where customers have switched from eddy current drives to VFDs, and then they had buyer's remorse a couple, 3 years down the road because hydrogen sulfide was getting into their VFDs and eating up cables and stuff like that. So we'd like to work with the customers when they're making a decision so we can provide all the information they might need and do any kind of calculation on what costs are. And that all starts with our manufacturer's representatives, like Southern Water is a good example.
Absolutely. We're here to start those conversations. And yeah, I mean, Dynamatic is worldwide. So, I mean, I think you were telling me just before we got on this call that you're going down to Mexico next week. So that's good times.
Fantastic. That is true. So that'll be very interesting.
Well, Gary, I appreciate your time today. We definitely hit a lot of topics, like I said, and there's plenty more to talk about when it comes to these eddy current drives. So look out for future episodes here on McGregor H.
You know, Taylor, just so you know, just to reiterate, at Dynamatic, we do all kinds of drives. We do eddy currents. That's been our bread and butter for almost 100 years. But we also do VFDs. We do VFDs in terms of coordinated control, also VFDs with very highly specialized panels for whether it's a water application or a drive application for, say, constant tension center winds and stuff like that. While I work in the municipal industry, I have colleagues that work in the industrial area. So we're readily available for any customer to like to talk to us about drives in general.
Awesome. Well, Gary, tell them how they can reach you. Give them your email if you want to.
Sure, that'd be great. You can reach me at gqueen at dynamatic.com. And let me repeat that since I speak Southern. It's gqueen@dynamatic.com.
Perfect. Well, thanks for talking to me today, Gary.
Taylor, thank you for your time.